Okay, folks, for this last learning goal in this module, I just want to very briefly talk about some of the various FTIR techniques. And you've done, I think, both of these techniques at this point in your education here, or at least two of the ones that I'm going to talk about. But I thought it'd be nice to at least give us some familiarity with that. So, one of the original types of ways to do FTIR spectroscopy was via transmission. And this is typically done with salt optics. So for example, this is some NaCl here, and you can see with this caption, a lot of pressure, a lot of money, and you can make an optically transparent sodium chloride optic. Pretty awesome. That being said, these are very difficult to use. Obviously, if you put on liquids that might dissolve the sodium chloride, you're going to ruin your optic, and it can be quite messy. So for example, this is kind of showing you what would happen to a spectra just from having like what's classified as an excellent optic, or one that's maybe cloudy, or one that's pitted. So you can see this really has deleterious effects on your IR spectra. And so the way this would go, right, you would put your molecule of interest there, you would sandwich it between two optics, and you would put those optics in a holder where the, let me get a red color, where the IR beam would then transmit through. And of course, you have to be able to take a background spectra beforehand. So your background spectra would just be two salt optics smashed together. And as you might guess, salt really likes to absorb water from the environment. So it is extremely difficult, if not impossible, to keep water out of your spectra with these salt optics. So luckily, we don't really use these too much anymore. So another technique that you probably are not so familiar with, but can begin to appreciate now, gas phase transmission. This is still very common and widely employed, and typically does use salt optics. So these would be salt optics. Now that last slide talked about using sodium chloride, sodium bromide, or even potassium bromide is the best, because potassium bromide is significantly less hygroscopic than sodium bromide, than sodium chloride. So typically we would see these with potassium bromide. And so now similarly, this is placed in this holder that would sit down in the sample accessory of an FTIR, where an IR beam can transmit right through. These long path cells typically have known path length. So we'll say L is typically known, so you can do quantitative stuff for this. And you might recognize these types of fittings. So the way that you would do this would be to put it on a Schlenk line. So all of those spectra that I showed you of like gas phase HCl or DCl or CO were low pressure spectra that were recorded in an apparatus very similar to this, and the molecules were put in this apparatus from a Schlenk line. So we also have things that are called long path cells, and these are this is a very similar idea where an IR beam will transmit through the cell. But now if you want to do stuff at a very, very low concentration and you need a long path length to detect anything, right? Remember, absorbance equals molar absorptivity coefficient times concentration times path length, right? So for a very low concentration, if you have an enormous path length, you can observe a spectra that way. And so these will typically have a convoluted set of optics that allow light to bounce around and give you a long path length. And because these are used for gas phase cells, you might even have some that contain like pressure gauges or other sample inlets and outlets to be used on a Schlenk line, or even with a pressurized cylinder. So now moving on to something you are more familiar with, the attenuated total reflectance, ATR. So this takes advantage of total internal reflection. So we can have single bounce ATRs or multi-bounce. So you have used a single bounce ATR in your careers here at Cal Poly Humboldt. So when you pipette your sample right on top of the IR, this is what you're doing. The beam is coming from underneath and undergoing total internal reflectance to generate what we call an evanescent wave. So it typically penetrates a very, very small distance into the sample, something like a couple of millimeters or less, and then makes it on to the detector. And because of the way of this technique, it can the sensitivity of it is okay in the single bounce form. It is excellent in the multi-bounce form. So in other words, when you get a special type of ATR crystal that is at the right geometry to give you total internal reflection, you get multiple evanescent waves through your sample, thus increasing the path length enormously. And this multi-bounce ATR crystal can be used to detect single molecular layers of molecules. So there's a lot of cool research out there where people have grown single molecules on the surface of their crystal. And because they get multiple bounces through these, that's like my cartoon, mono layer of molecules. Because of the multi-bounce, you can see an impressively small amount of material. So another technique that you probably weren't so familiar with before this class, but then maybe in lab, hopefully you've gained some familiarity. That's my favorite, the diffuse reflectance infrared Fourier transform spectroscopy technique, or DRIFS, as the acronym says. So in the DRIFS technique, there is a convoluted set of optics, including an elliptical mirror, that allows you to focus an IR beam onto the surface of a sample. Now, it is called the diffuse reflectance technique because our sample is typically not atomically smooth, so we get all of these random diffusely reflected beams coming off of the sample, and that's why we need this elliptical mirror to focus all of those stray beams back onto our detector. So this technique is really sensitive because the only IR beams that will make it off the sample are the ones that are coming directly off the surface. So this penetration depth is also typically single molecular layers. If we get a stray beam that kind of bounces deep into the sample, it's not going to make it back out. So this technique is widely employed in surface science to detect incredibly small changes at the surface. And that's what I do in my own research. So here is a schematic of what I do. So here is a cartoon of that drift cell. And in my research, we create a synthetic atmosphere. In this case, this is creating relative humidity. And we flow that relative humidity over the gas phase, over the top of a sample. And we can quantify how water will adsorb on single molecular layers. Additionally, our IR beam passes through the gas phase, which also contains our gas phase water. So this is like a typical spectra that we'll see where we've got rotational vibrational gas phase lines. We've got the condensed phase OH vibrational modes corresponding to a very small amount of molecules. And then we can also see the bending mode, and superimposed on top of the bending mode are more rotational vibrational gas phase lines. And so I'm not going to spend too much detail talking about what we do with this, but I just wanted to show that you can do really cool, sophisticated research with your garden variety FTIR spectrometer, assuming that you've got the right sample accessory. Okay, folks, that's it for this Module 9. I will see you in the next one.